my name is Henry Sengerman. These are the regular polyhedra, also known as the Platonic solids. So there's the tetrahedron with 4 triangular faces. There's the cube or hexahedron, which has 6 square faces. There's the octahedron with 8 triangular faces. There's the dodecahedron with 12 pentagonal faces. And the icosahedron, which has 20 triangular faces. And I've chosen the relative sizes of these so that the distance between the center of the polyhedron and the vertices is always the same. And this means, for instance, that the side length of the tetrahedron matches precisely with the diagonal of the square on the cube. And this means that the tetrahedron actually fits perfectly inside of the cube, with its vertices arranged sort of at alternating vertices of the cube. So 1, 2, 3, and 1 on the back. Those 4 vertices are the vertices of the regular tetrahedron. So these are the regular polyhedra.
These are the Platonic solids, named after the ancient Greek philosopher Plato. The Platonic solids are a very special type of polyhedron. Polyhedron is a solid constructed by joining polygons along their edges to enclose a region of space. Polygons then become the faces of the polyhedron. When all of the edges of a polygon have the same length, and all of the angles are the same, the polygon is regular. The Platonic solids are constructed from such regular polygons. Platonic solids are characterized by 3 properties. All faces are regular polygons. All faces are exactly the same, or congruent. And all corners are exactly the same. That is, the same number of faces meet at each vertex in exactly the same way. The cube is an example of a Platonic solid. All of its faces are congruent squares, and 3 faces meet at each vertex. This polyhedron is not a Platonic solid. Although all of its faces are regular triangles, and the faces are all congruent, 3 faces meet at this vertex, while 4 meet at this one. This solid has 2 different types of vertices. This figure is not a Platonic solid. All of the faces are the same, and the same number of faces meet at each vertex, but the faces are not regular polygons, since not all their sides have equal length. The faces of this polyhedron are all regular polygons, and 4 faces meet at each vertex. But they're 2 different types of faces, squares and triangles. So this is not a Platonic solid. Over 2,000 years ago, a mathematician named Euclid wrote a book called The Elements. This book is the basis for most of today's high school geometry courses. The grand finale of The Elements is a section about the Platonic solids, in which Euclid shows there are exactly 5. His explanation goes something like this. The simplest regular polygon is the equilateral triangle, How can equilateral triangles fit together to form corner pieces of platonic solids? 3 triangles can form a corner, and 1 more triangle closes the shape, forming a platonic solid with triangular faces. This solid is called a regular tetrahedron. Four triangles meeting at a vertex form a corner that looks like a pyramid. 2 of these corners can join to form a platonic solid with 8 triangular faces. Notice that all the corners are identical. This solid is called a regular octahedron. 5 triangles meeting at a vertex form a shallow dome. Joining 2 of these domes will not form a platonic solid, because not all of the corners are the same. Joining the 2 domes to a center band of 10 congruent triangles forms a platonic solid with 20 faces. It is called the regular icosahedron. 6 equilateral triangles surrounding a vertex lie flat. So no more regular solids can be made with triangular faces, because no more triangles will fit around a common vertex. The next simplest regular polygon is the square. 3 congruent squares can join to form a right-angled corner, like the corner of a room. 2 of these corners can be joined to make a cube. 4 squares meeting at a vertex lie flat. So the cube is the only platonic solid with square faces. The regular pentagon is the next simplest polygon. 3 of these meeting at a vertex form a corner. Now 4 of these corners together form a platonic solid with 12 faces. It is called the regular dodecahedron. 4 or more regular pentagons will not fit around a common vertex. Three regular hexagons coming together at a vertex lie flat. So no more solids can be made with just hexagonal faces. Regular polygons with more than 6 sides won't fit around a vertex at all. So, there are exactly 5 platonic solids: the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. The perfection of the platonic solids led Plato to write that they must represent the elements thought at that time to make up the world. Tetrahedron was fire, the octahedron air, the icosahedron water, and the cube earth. The 5th solid, the dodecahedron, represented the universe itself. Here are some skeletal views of the Platonic solids. The tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. Platonic solids occur in nature. Some crystals are shaped like platonic solids. Some microscopic organisms, called radiolaria, have skeletons shaped like platonic solids. Some molecules have the structure of platonic solids. The symmetry of these figures has fascinated not only the ancient Greeks, but also artists of the Renaissance, including Leonardo da Vinci, and the architects and sculptors of today. Cubes have been used as dice in games of chance from earliest times. Kubos actually means dice in Greek. All of the 5 platonic solids have been used as dice for thousands of years. Since all faces, edges, and corners of a platonic solid are exactly the same, any face has an equal chance of being chosen when you throw the dice. The relationships of the platonic solids to each other fascinated the mathematician and astronomer Johannes Kepler almost 400 years ago. He proposed a model for the orbits of the 6 planets known at that time, using spheres in which were inscribed the platonic solids. But later, the discovery of more planets and his own discovery of elliptical orbits proved this theory to be incorrect. As Kepler was working with one polyhedron inside another, he discovered duality. Every polyhedron has one related polyhedron, which is called its dual. Take a cube. Now put a point at the center of each face. This yields 6 points. Then connect the points on adjacent faces. These line segments form the edges of an octahedron, whose vertices are at the centers of the faces of the original cube. The octahedron is the dual of the cube. Now do the same with the octahedron. Put a point at the middle of each face, and then connect the points on adjacent faces. The 8 faces of the octahedron form a new figure with 8 vertices. It is the cube. The cube is the dual of the octahedron. The octahedron has 6 vertices and 8 faces. The cube has 8 vertices and 6 faces. The roles of face and vertex have been interchanged. This is what duality means. Take the icosahedron and put a point at the center of each face. Connecting the points on the 5 faces surrounding a vertex forms a pentagon. Connecting points on all adjacent faces makes the dodecahedron. The dodecahedron is the dual of the icosahedron. Now put points at the centers of the faces of the dodecahedron. Connecting the points on the 3 faces surrounding a vertex forms a triangle. Connecting the points on all adjacent faces makes the icosahedron. So the icosahedron and the dodecahedron are duals of each other. Here's another look at duality. Each vertex of the cube corresponds to a face of the octahedron. The cube is the dual of the octahedron. Each vertex of the octahedron corresponds to a face of the cube. The octahedron is the dual of the cube. The cube and the octahedron are duals of each other. The icosahedron and dodecahedron are duals of each other. Just like the 4 other platonic solids, the tetrahedron also has a dual. What is it?